this video, I'm going to be talking about higher order partial derivatives. So the setting is, as always, f from u to r is a function. Now suppose the partial derivatives d1f, d2f, dnf exist on u. So this function is differentiable with respect to each of the variables throughout u. Then of course I can consider this dif as a function from 0 to r. So I get new functions d1, d2, d3 dn, which are themselves functions from the open set u taking values in r. Now I can repeatedly take more partial derivatives. For instance, I could take d1, d2f. This is exactly what the notation suggests. You first differentiate with respect to the second variable. You will get a function d2f from u to r. Then you differentiate with respect to the first variable of this new function. And in this way, repeating this process, you can get many combinations of derivatives. In a standard multivariable calculus course at the undergraduate level, you must have definitely come across horrible expressions that look something like this: del 4f by del x squared del y del z. So this is a typical expression that says you first differentiate with respect to z, and then you differentiate with respect to y, then you differentiate with respect to x, then again with respect to x. So I'm going to assume that you are familiar with such notations, and I'm not going to use such horrible notation in this course. We will use the more elegant multi-index notation, which will become very useful when we prove Taylor's theorem down the line. So let me give the definition of multi-index notation. It's a bit involved and it takes a bit of getting used to, but once you get used to it, you will prefer this notation over the classical notation for partial derivatives. So a multi-index alpha is just an element of the natural numbers union set with 0, Cartesian product with itself, order n for some n. In the natural numbers. So a multi-index is just a tuple of non-negative integers. The order or degree or length of alpha, this is denoted by mod alpha, is just the sum of the various entries. It's just alpha 1 plus alpha 2 plus alpha n, where alpha is equal to alpha 1 comma alpha n. So if you take this tuple alpha 1 to alpha n and you want to find out the length, you just take the sum. So if alpha is of length n and x equal to x1 to xn is an element of Rn, then we define x bar alpha to be x1 power alpha 1 multiplied by x2 power alpha 2 xn power alpha n. And finally, we define alpha factorial to be alpha 1 alpha 2 alpha n. Okay, so these are the various operations that you can do with multi-indices. Of course, you can add multi-indices. I'm not going into that because it's just component wise. One more thing I need to define for you. If f from u to r is a function, then we define del alpha f, the alpha partial derivative of f, to be nothing but del mod alpha f by del x1 par alpha 1 del xn par alpha n. Okay, so of course when the relevant partial derivative, when the concerned partial derivative exists, otherwise it makes no sense. When the concerned partial derivative exists. Okay. Now, so such an del alpha we say is actually an mod alpha order partial derivative operator. Okay. Now observe that the way we have defined this partial derivatives using multi-indices, there is no way to do del squared f by del x2 del x1. This is simply not possible, but this is not such a big deal because we will soon prove a theorem which says that the orders won't matter once you put a mild hypothesis on f. So before I do that, let me just make a very important definition which is going to be used throughout this course. This is the definition of smoothness classes. So again, f from u to r is a function. We say f is of class CKU or CK smooth. So here k is a natural number. CK smooth on u if all partial derivatives up to order k exist and are continuous. Okay, then we say that the function is of class CKU or CK smooth. Okay, so not only do you require the derivatives to exist, the derivatives must be continuous. That's important. Okay, we also say f is C infinity smooth or of class C infinity u or just plain smooth without any further qualifications, or just smooth on u if all partial derivatives of all orders exist. Note there is no continuity requirement here. The continuity requirement is automatic. I want you to prove that as a simple exercise. Okay, so coming back to the situation I described in the previous slide, where there is no way to express del squared f by del x2 del x1 in our concise notation involving multi-indices. This is not much of an issue because in most scenarios the function will be well behaved enough so that these things are equal. So that is a famous theorem which you must have learnt in multivariable calculus, but probably without proof. This is called Clairaut's theorem. So the setting is again as follows. Let f from u to r be such that d2 d1 f and d1 d2 f both exist and are continuous. Then of course I am going to write both are equal, so I am going to write in that elaborate notation del f by del x1 del x2 is equal to del f by del x2 del x1. Both partial derivatives are equal. The second order partial derivatives are equal. Now there are weaker versions where you put enough conditions on one pair of partial derivatives to automatically ensure that the second pair of partial derivatives automatically exist. So I'm not going to prove those more general statements. This will be practically sufficient for all applications. So I'm going to make a simplification and leave it to you to prove the general case. This is actually without loss of generality, but I'm going to ask you to check why this is really without loss of generality. We will assume u is subset of we will assume U is subset of R2. So we are only going to consider the two variable case. The general n variable case can be easily reduced to this situation, which I am going to leave to you. So let the point x comma y be in U. Okay, of course I didn't mention, it should have been obvious or continuous on the whole of U. So let me just add it so that there is added clarity. So take this point x comma y in U and let this another vector pair of numbers h comma k be not equal to 0, not equal to actually this is a bad way of saying it. Let h comma k be in R, both h comma k are not 0. Okay, now so let's draw a vague picture. This picture will sort of guide what is happening. So you have this domain U. I am focusing on this point y. What I'm going to do is I'm going to consider h and k so small that this entire rectangle, this is x plus h, this is x plus h comma y, this is x plus h comma y plus k, and this is x comma y plus k. So I'm going to choose h and k so small that this entire shaded rectangle, in fact the closure of that shaded rectangle is fully contained within the domain U. So I'm going to only consider h and k so small. Okay, now what I'm going to do is I'm going to compute the values of this function on the vertices of this rectangle I have just drawn. So what you do is you define this new function g of t to be equal to f of t comma y plus k minus f of ty. Okay, this is a one variable function and this is certainly defined whenever t is an element of x comma x plus h. Okay, of course I'm treating h and k as positive. I want you to go do the same arguments. It will be quite similar whenever h or k is negative. So this actually should be or x plus h comma x. If h were to be negative, this function g will be defined in the closed interval x plus h comma x. I'm not going to treat the negative case. I'm just going to consider the positive case, and the proof in the negative case is exactly the same. So by mean value theorem, we can find t1 in, let's say, x comma x plus h. It could be x plus h comma x. That's really the only change you will have to make when adapting the proof to the negative case. We can find t1 in x comma x plus h such that g of x plus h minus g of x is just g prime at t1 times h. We can apply the mean value theorem on this interval simply because we know that the partial derivative for d2 d1 and d1 d2 to exist, both d1 and d2 must exist, and they must automatically okay, I'm not going to talk about continuity. Both d1 and d2 must certainly exist, and once d1 and d2 exist, we can certainly apply this. Okay, here for instance only d1 is needed. The existence of d1 is needed, but the existence of d2 will be quickly needed in the next few steps. Okay, so what have we done? Expanding out this definition of g of t, what we actually get is the following: f of x plus h comma y plus k minus f of x plus h comma y minus f of x comma y plus k plus f of xy. Okay, so this is the expanded out version of what I have done. Just wait a second, let me just erase it. I think I wrote this wrong. Let's just do it the whole thing. So when you substitute g of x plus h would be nothing but f of x plus h comma y plus k minus f of x plus h comma k f of x plus h, x plus h comma y, not k, right? And similarly, g of x would be just f of x comma y plus k minus f of xy. And when you subtract this, you will get a minus sign here and a plus sign here, and we can erase this. Yeah, I wrote it correctly, not bad. Okay, I wrote it correctly. So you get f of x plus h comma y plus k minus f of x plus h comma y minus f of x comma y plus k plus f of xy. What does our result say? This application of mean value theorem, this is just g prime of t1 times h. That's what we had got from the application of mean value theorem. Okay, now expanding this out in terms of partial derivatives, this is just h of d1 f of t1 comma y plus k minus d1 of t1 comma y. This is just expanding out by partial derivatives. Now we have assumed that d1 itself is differentiable in the sense that d2 of d1 does make sense. So now applying the mean value theorem to the function d1, we get this is nothing but hk times d2 d1 t1 comma u1, where u1 lies in between y and y plus k. Okay, now what we are going to do is we are going to compute this complicated expression f of x plus h comma y plus k minus f of x plus h comma y minus f of x comma y plus k plus f of xy in a different way. What we are going to do is we are going to consider the function, the new function f of x plus h comma y minus f of xy. In the first case, we considered the function f of we considered the function g of t equal to f of t comma y plus k minus f of ty. So this time we are going to consider f of x plus h comma t, minus f of xt. And we are going to apply the exact same argument we have done, and we will be able to conclude that this big expression is in fact equal to hk d1 d2 here I forgot an f, d1 d2 f of t2 comma u2, where again t2 and u2 are numbers in between x and x plus h and y plus k respectively. Okay, so the net upshot is d1 d2 f of t1 u1 let me go back and refer to the previous one. Yeah, hk d2 d1 f of t1 u1 is equal to hk d1 d2 f of t2 u2. I hope I got that correct. I did not mess up anything. Yeah, not bad. Okay, so h and k were assumed to be non-negative, so these two can be cancelled out. And notice that this will yield t1 u1 t2 e2 irrespective of how small h and k is. If I shrink h and k, I would get different values of t1 u1 in between x and x plus h and y plus k respectively, but this equality will be still true. Taking h comma k to 0, both of them to 0, and by using the fact that the partial derivatives are continuous, we immediately get that d2 d1 f of xy is equal to d1 d2 f of xy as claimed. So the proof just involves taking the differences of the values of the function on the four vertices of a rectangle in different ways and applying the mean value theorem twice, and then taking h comma k to 0. That's the basic idea of the proof. So I have solved it only in the two variable case. Now I'm going to leave a final exercise for you to finish. The exercise says show that if f is of class CKU, then we can take partial derivatives. It does not matter, I will trace it in a better way. We can then the order of taking derivatives, partial derivatives is immaterial for all partial derivative operators up to order k. It really doesn't matter. In the exercise in the notes, I've given you an explicit example where taking the order of partial derivatives will give you different result. This is a scenario where the hypothesis of Clairaut's theorem will not be satisfied. This is a course on real analysis, and you have just watched the video on higher order partial derivatives.